You certainly convinced me that broad spectrum, full spectrum lighting is superior to narrow spectrum LED lighting and far superior to HPS. My job here today is to review the basics of lighting for plants and also for commercial growers of plants. And I think in reviewing those basics, it will help those who are interested in this topic to understand why Ash is correct about the statements made. So I would like to start out by listing the 5 cardinal factors of plant growth and development. These are 5 environmental factors that are absolutely required for plants to complete their life cycle. First and foremost is always light, the energy and the signaling medium for plant growth, temperature. Plants do not regulate their own internal temperature like we humans do, so they are totally at the mercy of their environment. And in a controlled environment, the grower has to provide that. Mineral nutrients, there are about 13 of them that come from the soil or from hydroponics in the case of CEA. Water, the delivery medium, and also helps to regulate plant temperature through evapotranspiration from leaves, and atmosphere. Here I'm talking mainly about carbon dioxide for photosynthesis and oxygen for respiration. Now, as I said, these variables are absolutely required and they cannot be substituted by anything else. They are semi-controlled in greenhouses, and in indoor agriculture, they have to be totally controlled. And the difficult thing is they do not act independently. They are totally interdependent upon each other. And so it becomes difficult just by varying one of them to predict what's going to happen. So this is a hard job for the researchers. Now, there are 3 dimensions of plant lighting. Plant quantity or intensity gives you the biomass of the plant. The light quality or the spectrum gives the morphology or the development of plants. And the light duration or photoperiod controls things such as flowering. But it's not that simple. Light quantity also affects morphology and flowering. Quality does as well, and so do the duration. So even within light, the 3 parameters of lighting, they are also completely interactive with each other. Okay, so here I would like to go over some metrics that you will hear with respect to light and plants. We're talking about the portion of the electromagnetic spectrum between 400 and 700 nanometers, which is all visible. It's in the visible region of the spectrum, but the part that drives photosynthesis, and we call PAR, is between 400 and 700 nanometers. And recently it's been proposed that we go a little beyond that to include wavelengths of the far red, which I'll explain later. The intensity or photon flux density is given in micromoles of photons per square meter of absorbing surface per second. If you go and include the far red, then that ppfd becomes total photon flux density, same units. But plants integrate the light that they absorb over the entire day. And this is what's important, so that we've come up with the concept of daily light integral. And instead of talking about micromoles per meter square per second, we're talking about moles of light per meter square per day. This is just like chemistry. And even though we humans see green light and it's measured in foot candles or lux, we don't recommend that at all for plants, because the human eye responds maximally in the middle of the green, 555 nanometers, and that's not the best for plants. There would be huge errors. So recommend not using old foot candle or lux meters for plants. Here are some units. The green one is the quantum sensor that integrates from 400 to 700, and it's really the area under that curve that's giving you the PPFD. And then two wavelengths that are really important are red and far red, because they drive the phytochrome system, which is extremely important for development and things like flowering. And so here we have two spectra showing both the intensity and the photon flux. And you can see for the sunlight, it's pretty uniform, the green, across the 400 to 700 nanometers. So going from blue to green to red, and then beyond that, there's still quite a bit of far red light. Now, this is midday solar light, but the red is the energy. And you can see that the most energetic wavelengths in the PAR start with the blue, comes down through the green, and the red, and the far red. So here is a very important curve, and the green one, again, is overlaying the solar spectrum. But the black curve is the relative quantum efficiency of each of the wavelengths of the PAR individually, separately, when they're given discretely. And you can see that the red from 600 to 700 has the highest peak. There's a secondary peak in the blue from 400 to 500, and then the green lags a little bit. But surprisingly to some people, there's quite a bit of photosynthetic efficiency of green light. This really bothered people for a while, because chlorophyll A and B don't really absorb hardly any green light at all. But plants do. They have accessory pigments and carotenoids that do. So blue, green, red, they're all a factor in driving plant photosynthesis. So now this phytochrome, this photoreversible pigment, if you give PR, the inactive form, red light, it converts to the active PFR form. If you give it far red light, it goes back from the active to the inactive form. And you can see the overlap in the diagram of the PR and PFR spectra. They absorb more than just red or blue, or far red, sorry. And they overlap with each other, so any broadband source with a given red, far red ratio is going to give some kind of a plant response. And this becomes very important in growth and development, things like flowering. And there are a lot of ornamental greenhouse growers that leverage this to control flowering, both to prevent it and then to induce it when they want to. And then the cryptochrome, you see that blue spectrum, that's mainly peaking in the blue. And that drives a lot of things like phototropism and stomatal movements, especially the opening of stomates on leaves. And then, so here I just insert 3 monochromatic discrete LED spectra to show how you can select them so that they coincide with the peaks of these photosystems. And this can be very useful and energy saving in controlling plant growth and development. And then finally, the absorbance, the reflectance, and the transmittance. You can see in the blue region from 400 to 500, it's mostly absorbed. So that goes back to Ash's first slide showing that the the outer leaves in a multi-layered leaf canopy are absorbing most of the blue. They are the red also from 6 to 700. In the green, 5 to 600, you're getting some transmittance to the next leaf level. You're also getting some reflectance. And when you get over into that far red region, that's very important, actually very little of it is absorbed. That's that little gray area. It's mostly reflected and it's mostly transmitted. So plants evolved to utilize the different wavelengths of light for their various applications. I don't know what I did there. Okay. Now I'd like to transition now into greenhouse growing and say that in greenhouses we do what's called supplemental lighting, supplementing free solar energy, and that's usually relegated to reproductive or fruiting crops because they have the highest light requirement, and you always want to take advantage of the free solar energy whenever you can get it. And the amount of supplemental lighting needed shifts seasonally, and you still always try to keep it as low as possible. Okay. Now I'd like to say that it's not as simple. Location, it's not just latitude. That is a very important one, but also the climate and the weather of the local area, and then things like the energy cost, because that will affect it. And so these all lead to different strategies for supplemental lighting, especially for off-season lighting, for outdoor crop growth. And the way it turns out is that a commercial grower who wants to be producing year-round almost cannot afford not to do supplemental lighting. So here's a very interesting graph. What it shows is differences in day length throughout the year. You have your autumnal and vernal equinoxes, when the day length and the night length are each about 12 hours long. And then you have your summer solstice, where it's the longest day of the year, and then your winter solstice, the shortest day of the year. And you can see that they overlap at the equinoxes. So here in New York, we're just a little higher than that 40-degree north one. And you can see what the maximum day length of the year is. It's around 15 hours, but then it gets down very short in the winter. So this varies sinusoidally throughout the year. It varies back and forth. And that's just latitude. And in the southern hemisphere, it's the exact opposite of this. But that's one aspect, latitude. And in the winter to the late spring, greenhouse growers have to do supplemental lighting if they're going to grow a crop year-round. And here, for the United States, these colors show the integrated daily light integral. Remember, this is moles of light per meter square per day and how it varies. So if you look at June, the longest day of the year occurs around June 21st. And for here in New York, it looks like we're looking at very high DLIs, maybe 40, 45 moles. That's enough to grow most crops outdoors. And in December 21st, it gets way down to 10 to 15. But these are outdoor DLIs. What happens if you go into a greenhouse? And here are data for a greenhouse at about 40-some degrees north latitude. Look at June, a sunny day, the integration under the curve, and then look at the cloudy day in the greenhouse in June. It's cut in half or less. But when you go to December, comparing neither the sunny day nor the cloudy day in the greenhouse is going to give you enough light. So if you're going to be a productive, consistent commercial grower, you have to do supplemental lighting. Now here's a compilation of a lot of greenhouse crops. Most of them here are ornamental. And there are a lot of growers who still grow ornamentals in greenhouses. The yellow bars give you the minimally accepted quality for the DLI. The green, it's okay. And then the red is your very high quality product that you're going to sell. And you can see how it varies by species and cultivar. And for high quality, we're talking about some very high DLIs here, around 30. And if you're going to do that in a greenhouse where your DLI is somewhere between 5 and 10, you need a lot of help from supplemental lighting. And here it is for vegetables. And I have done a lot of work with tomato myself. The minimal DLI is 20 moles per meter square per day, and then up to more than 30 is recommended. So this is a lot of light. And if you're a commercial grower in a greenhouse and you're into that winter weather, cloudy, you're going to have to do supplemental lighting if you're going to stay in business and make any kind of a profit. And then add greenhouse roof angle and the sun coming up with a very steep angle in the morning and going down with a very steep angle. In that graph on the left, you can see that even at midday with the sun coming straight down, you're still losing 10% light going through greenhouse glass. But throughout the course of the day, as you go towards sunset, as that angle gets greater and greater, it bounces off the glass. And so I've written in the integral over the course of a day, 100% of light incident on that greenhouse, only 76% of it is going in. So you've got that factor in the greenhouse business too. You have changing solar angle and roof angle. You've got latitude, and then you've got weather on top of all of that. And then finally, I'd just like to state, here are two spectra from the UV through the far red of what the midday solar spectrum looks like. Very high in blue, it's scattering everywhere. Pretty high in green, red, and in far red. But at the end of the day, when the sun is going down, the blue is backscattered into space, the red is way down, and the far red actually goes higher than red. So think of that phytochrome photoequilibrium, how that changes. And this occurs naturally. I leave you with the question, do we want to eventually get there with the greenhouse supplemental lighting? So what could adoption of supplemental lighting do for growers, greenhouse growers, who want to be more competitive and more profitable? Well, it's going to extend the capability to grow your crop of choice year-round, productively. It's going to make the production cycle more predictable and controllable. And it will improve the quality of the product, whether it be an ornamental product or a food product. And it may shorten the production time of the crop if you do the supplemental lighting correctly. It could also enhance the yield. And with all of those things, it could also affect the price point and the market value of the crop that you will harvest. So to finish up here, let me just mention, echoing some of what Ash said, the industry standard has been the high-pressure sodium lamp. It has advantages, it has disadvantages. You can get high intensity with HPS. Typically, you go to 1,000-watt lamps that are mounted high in greenhouses. Relatively long lifespan compared to predecessors, but not relative to LEDs. Some growers like it because they're so hot it cuts down on their heating costs in the winter. It's an effective PAR source, but not the most effective. It has an historically lower capital cost than for LEDs. The disadvantages are the very high electrical energy costs, the fact that the long wave radiation creates a lot of air heating, and if you're not growing in the winter, it will cost you more if you have to do cooling with all of that heating going on. The wave band is kind of a mismatch. It's not very efficient, and there are disposal issues that cost money. It contains mercury, for example. LEDs, of course, are solid state, low volume and mass. They have 2 lifetimes, one of the diode and then the other of the electronic mounts. They operate on much lower voltage DC, and the emitter surfaces are cool enough that you can actually get them fairly close to the plant tissue, and you can defeat the inverse square law that says that intensity increases or decreases with the inverse of the square of the separation distance. So you don't have that heat of the HPS lamp, and you can get in fairly close. Disadvantages, they're getting less and less. The initial capital investment is coming down consistently. Dense arrays may require active heat sinking, but you don't typically encounter that in the greenhouse environment. And I think with the flip chip design, that's already taken care of. Where we're going to go with the need for variable spectra throughout the life cycle of crops or with different crops, I'm not sure. It would be really nice to have dimmable LEDs and also be able to change the red and far red ratios for sure, and possibly also the blue and the green. And I think this is all coming with the evolution of the industry. A couple of shots of overhead supplemental lighting of high wire tomato in greenhouses, as well as interlighting of a cucumber crop in the greenhouse. Interlighting or intra-canopy lighting is where you put the light right into the canopy, and they are cool enough that you do not have to worry about scorching the crop. That's the great thing. So for crops that are mutually shading, they have layers of leaves, you can put the interlights or intra-canopy lights right in there. Here is a summary of what each waveband does. Red typically dominates on arrays. Blue is very complex. It's the second most efficient in photosynthesis. It does many other things, especially promoting pigment, antioxidant, and phytonutrient accumulations. Adding far red, we know, promotes stem elongation, leaf expansion. And recently it has been found that it also drives photosynthesis when it is applied simultaneously with shorter wavelengths of PAR. So the two together, you get more growth, but you also get more leaf expansion. So it's kind of a double benefit. More photosynthetic surface and more photosynthesis, but the far red has to be simultaneous. UV, still looking at that. It generally prevents tumorous or intumescence growth. Green penetrates deeper into canopies. Ash showed you good slides of that. And so where you have multi-layered crops, you actually get more photosynthesis by having some of that green. But the white LEDs have all of these things together. And plants did evolve under broadband solar light. So they already have the genes and the gene products and the mechanisms for responding to full spectrum light. Back in the early 2000s, Haigh's law was derived, and it showed that for every decade that the LED cost was coming way down and the efficacy was going up. That cuts off before where we are now, but the trend is still going. And here, the graph on the right shows these photosynthetic photon efficacies in micromoles per joule, micromoles of light output per joule of energy of electrical input. And it's as a function of forward drive current, but you can see that they're getting way up there into the twos. That was published in, I believe, 2014. They're even higher now, and Ash showed you some graphs of them being over 3, which is a really good level. In the middle graph there's a projection that the efficacies of LEDs is going to go way up before it plateaus in the 2030s. And for both phosphor-coated and for the newer color mixing ones, it's going to continue to go up. And if you see that black line down there, the HPS photon efficacy is stuck right at 1.8. So the LEDs continue to move ahead of that. So what's needed? CapEx, OpEx combinations that are cost competitive. Ash also showed you some dollars and cents comparisons of that. Superior product quality, and what I mean by product is not lights, it's plants. It's product quality in terms of taste, flavor, texture, phytochemical, healthy content. Okay, and some recommendations. I think broadband LEDs are a good way to go. And the capital costs are coming down every year. You've already seen that the CapEx, OpEx combination in over a 5-year period of time is superior. And a major advantage would be for LED supplemental lighting to become broadband, have high efficacy, and be cost competitive with its competitors.